All right, welcome to this explainer. Have you ever just looked down at the ground beneath your feet and wondered what is actually going on way down there? Do you imagine it's just a solid, boring ball of rock, or is it something far more dynamic? Today we are unpacking this chapter and setting off on a massive investigative journey into the hidden mechanics of our planet. We're going to dive into the ultimate planetary detective story and figure out exactly what is happening deep, deep inside the Earth.
But right out of the gate, we run into a really massive mystery. Think about this for a second. The Earth's radius is roughly 6,378 kilometers. Yet the absolute deepest hole humanity has ever managed to drill, the Kola Deep Drill Hole up in the Arctic, is only 12 kilometers deep. That's it. They literally had to stop digging because it was so intensely hot it was melting their drilling equipment. We have barely even scratched the outermost surface of the Earth. So how on earth do scientists actually know what's going on thousands of kilometers below us?
Well, here's our roadmap for figuring it out. 1. The unseen planetary mystery. 2. Earthquakes as our ultimate clue. 3. X-raying the Earth with waves. 4. Revealing Earth's layered interior. And finally, 5. Volcanoes as Earth's pressure valves.
Okay, kicking things off with Section 1, the unseen planetary mystery. Let's find some clues to our planet's deep secrets.
So, since we can't exactly take a submarine down into the Earth's core, our direct sources of evidence are surprisingly limited. We've got surface rocks, and we have mining, like the incredibly deep gold mines in South Africa that go down maybe 3 or 4 kilometers. But beyond that, it gets way too hot to keep digging. We also have that deep ocean drilling maxing out around 12 kilometers, and of course, the occasional volcanic eruption that brings some molten magma up to the surface for us to study. Because direct drilling is physically blocked by this extreme searing heat, scientists have to rely heavily on indirect sources. It's like a giant puzzle. They look at how density and temperature increase the farther down you go. They even study meteors, because those are made of very similar planetary building blocks. And they analyze things like gravity anomalies and magnetic fields to infer where all the mass is hiding far below us.
Which brings us to Section 2, Earthquakes, the ultimate clue. The Informant revealing Earth's hidden depths.
To really picture that deep interior, we need something seriously powerful, and that's earthquakes. Let's look at how this energy is actually generated. Earthquakes happen when energy is released along a fault, which is just a sharp break in the crustal rocks. So, step 1. Imagine the rocks on either side of this fault are being pressed together, and friction just locks them in place. Step 2. As tectonic forces keep pushing and pushing, these gigantic rock blocks deform over time, building up immense, incredible strain. And finally, step 3. The pressure to move completely overcomes the friction, and the rocks violently slide past one another. This sudden snap releases a massive wave of energy in literally all directions. The exact point deep inside the Earth where this energy releases is called the focus, or the hypocenter. And the point directly above it on the surface, you've probably heard this term, that's the epicenter. Now on the left here, you see the damaged Amman Setu Bridge in Uri, which is just completely deformed. And on the right, an absolutely devastated landscape leveled by a tsunami. Keep in mind, an actual earthquake might only last for a few terrifying seconds, but the solemn reality is that the surface effects, everything from structural collapse to the soil literally turning to liquid to massive tsunami waves generated by underwater tremors, are absolutely devastating. Let's move on to Section 3, X-raying Earth with waves, using planetary sonar to map the unknown. Now, this is where it gets incredibly fascinating for our planetary detective story. Scientists realized they could use these earthquake waves like a giant planetary X-ray to map the unknown depths. When a quake happens, it generates these things called body waves that travel straight through the Earth. There are 2 main types you need to know. First, P waves, or primary waves. These are the sprinters. They're the fastest. They vibrate parallel to the direction they travel, kind of stretching and squeezing the rock, and they can pass through gaseous, liquid, and solid materials. Then we have S waves, or secondary waves. They're a bit slower and vibrate perpendicularly, creating crests and troughs. But here is the absolutely crucial point of this entire chapter. S waves can only travel through solid materials. They absolutely cannot pass through liquids. This single, highly specific characteristic is the ultimate key to unlocking the Earth's interior structure. So when seismographs all around the world record these quakes, scientists notice these weird shadow zones where the waves simply don't show up at all. Because the interior of the Earth has all these different densities, the P waves refract, they bend as they travel through. This bending creates a very distinct dead band between 105 degrees and 145 degrees away from the epicenter where 0 P waves are recorded. This perfectly proves that there are dramatic shifts in density deep inside the Earth.
But check this out.
The S-wave shadow zone is massive. It covers a little over 40% of the entire Earth's surface. S-waves hit a boundary at 105 degrees and just entirely disappear. Boom, gone. They don't bend and pop up later, they are stopped dead in their tracks. Because we know for a fact that S-waves can only travel through solids, this massive shadow zone definitively proved to scientists that a gigantic liquid layer exists deep inside the Earth. No submarine required.
All right, Section 4. Earth's layered interior revealed. Let's look at the structure hidden right beneath our feet.
By analyzing literally thousands of these seismic waves, our planetary detectives completely cracked the case. Here's the Earth, neatly categorized into its descending layers based on the chapter's data. First, we have the crust. That's our home. It's brittle, solid rock, ranging from just 5 kilometers thick under the oceans to up to 70 kilometers thick under huge mountain ranges like the Himalayas. Below that is the mantle, plunging all the way down to 2,900 kilometers. It's solid, but the upper portion actually contains this weak, semi-fluid zone called the asthenosphere. Then, we hit that boundary we found with the S-waves. The outer core, starting at 2,900 kilometers deep, is entirely liquid. And finally, the immense, crushing pressure at the very center forces the inner core back into a solid state. It's a dense, heavy ball made mostly of nickel and iron, which is often called the knife layer.
When you actually visualize these massive, layered structures stacked together like a cross-section, it's a profoundly humbling reminder that we live on an unbelievably thin outermost skin. It's kind of like the skin on an apple. The entire realm of human existence is just perched on that tiny, microscopic top line of the crust. Now, to really understand our surface world, we need to know one specific term from the source material: the lithosphere. The lithosphere includes the brittle crust and the very uppermost, solid part of the mantle, going down about 200 kilometers. Make sure you take away this concept, it's super important. This lithosphere makes up the solid tectonic plates we stand on, and these plates are essentially just floating and moving upon the weaker, slushier asthenosphere right beneath them.
And that leads us perfectly into Section 5. Volcanoes, Earth's pressure valves. How all that interior heat actually escapes to the surface. So, with a super thin crust just floating over a dynamic hot mantle, that interior heat has to escape, and it often does so violently. When rock melts in the asthenosphere, it finds a weak spot and erupts onto the surface. We call it lava. And this creates an incredible variety of volcanic forms. We have shield volcanoes, like you'd see in Hawaii. These are huge, gently sloping mountains made of really fluid basalt lava. We've got composite volcanoes, which erupt highly viscous lava and ash, building up those tall, classic, super explosive mountain peaks. Then there are calderas. These are so violently explosive that they literally collapse back in on themselves, leaving massive depressions in the earth. We also have flood basalt provinces, where highly fluid lava just pours out over thousands of square kilometers, kind of like the Deccan Traps in India. And finally, the mid-ocean ridge volcanoes. This is a massive 70,000-kilometer-long underwater volcanic system that stretches through all of our ocean basins.
You can really see the contrast between these environments here. On the left, we have the classic, relatively smooth profile of a shield volcano, which is built up from slowly oozing fluid lava over time. But on the right, look at that highly rugged, extensive volcanic landscape forged by cooler, stickier, way more explosive eruptions. And what's wild is that these aren't just destructive events. These eruptions of interior heat are literally building and shaping the varied, dramatic topographies of our world. They actually create the very land we live on.
Honestly, if you take away just one crucial thing from this explainer today, make it this. The solid, seemingly peaceful ground beneath our feet is actually a thin, fragile raft. We are literally riding on a sea of dynamic inner turmoil. The beautiful, peaceful landscapes we see every single day are entirely the product of violent, unseen forces churning thousands of kilometers below us.
I want to leave you with this final thought, straight from the chapter we're exploring today. The configuration of the surface of the Earth is largely a product of the processes operating in the interior of the Earth. Knowing that a massive liquid ocean of iron and rock is just sloshing around beneath you, generating huge magnetic fields and pushing giant tectonic plates, what other massive, hidden processes do you think might be quietly reshaping our world right under your feet, even as you watch this? Think about that the next time you take a walk outside. Thanks for joining me on this journey to the center of the Earth.